And if something piques your interest, you're welcome to ask me about it, because there's no way I can cover it all in 45 minutes. And then I want to give you a sneak preview of our 2023 through 2029 strategic plan, and give you some highlights. And this plan is going to come out very, very soon. I just made the final demands on our company that is working with the layout of it. And once that gets finalized and we can get it up on the website, we'll send it out. And then you can read about it in all its gory detail. But here I'll at least give you the highlights of it so you have an understanding of what it is that we're hoping to do in the next 6 years. And then I really would like to give you some research updates. So there's been some stuff that's been going on at SNOLAB that's kind of really, I mean, I think the science at SNOLAB is so awesome. It's why I gave up my full faculty position with tenure and everything to move here to Canada and lead this lab, because I really like talking about the science a lot. So I'm a scientist at heart. And so I thought I would try to highlight sort of 3 of our larger programs, although it's not everything. And I can't even talk about all the experiments in those programs, but dark matter, neutrino, and biology. And so this is not going to be a deep dive. It's going to be a high level look at these experiments. Any of these experiments and programs, you could have a whole hour colloquium on. But I just want to give you a sampling of what we're doing. Then I want to talk to you a little bit about the SNOLAB infrastructure and what we have underground, because there are actually a lot of really cool, neat things that we have that you might not think about in it. It's something that you might have. Like, we actually have a liquid nitrogen plant underground, and because of our experiments. So there's a lot of things that I think are neat. And then I want to talk a little bit about our commitment to a skilled workforce before making a few closing comments. All right, so that said, let me introduce SNOLAB. So you guys probably know more than anybody else where SNOLAB is. It's essentially 4 hours north of here in Sudbury, Ontario. It's located 2 kilometers underground in an active mine that's run by a company called Valet, who is one of our partners. We wouldn't be able to do the amazing things that we do underground without our partnership with this mining company. But having an active mining company, of course, presents its own challenges when you have experiments underground. You can imagine there's blasting and things going on, but it's definitely much more of a partnership. We are operated jointly by a number of universities. So the Valet Mining Company, as I said, is an important partner for us, but so is Carleton University, the University of Alberta, Laurentian University, which is located right in Sudbury, the Université de Montréal, and Queen's University. And our funding partners are numerous, both federally and within the province, and locally, the city of Sudbury itself helps to fund some of our programs. So why underground? This is a great thing. Like, we certainly could do physics experiments a lot easier in a lab right here at your very own university. Well, it turns out that there is a growing community of users who need a very shielded, I will call it quiet environment. And what I mean is that they need to be protected from the cosmic rays that are constantly bombarding the Earth. They also need to have a very sort of radio pure, radio quiet, if you will. I'm using radio purity, radio quiet in that sense, in order to operate their experiments, because what they're doing is looking for such rare events that just the ordinary background radiation of our ordinary everyday lives is like more than their experiments can handle, if they ever hope to see a signal. And so SNOLAB, although it's not the deepest mine in terms of what the overburden above us is, it actually is the laboratory in the world that has the lowest flux of muons. Okay, so Zheping lab is deeper than us, but it's actually in a mountain. And so when you calculate the muon flux underground, you have to take into account that their overburden isn't just straight up. It also comes from the sides. We're located underground with essentially a flat surface. And so that gives us the advantage in muon flux, and why it is that in the number that scientists really care about when they're building these experiments, Sudbury wins. Of course, it does mean that there are more challenges in trying to get your equipment into our lab, because it all comes down a shaft. It essentially has to be disassembled and reassembled underground. Even as things as simple as a boom to lift to go up to high places, we have to disassemble it, put it in carts, train carts, bring it into the lab, and then reassemble it underground. So where a lab like Jepang, you know, you can kind of just drive in off the side of a highway and everything's there. So the accessibility might seem a little bit easier, but the price you pay is, of course, the muon flux. So in addition to being underground, so it is mines are very dirty in general kind of environment. And I said, not just the muon flux that we care about, but it's also the cleanliness. So SNOLAB is a class 2000 clean room underground. So what that means is that when you actually come in to do work in our mine, and those of you who are there regularly know this quite well, it's one of the things I kind of like about the job. I can get up in the morning, and if I'm going underground, I don't need a shower or anything. Just throw on a pair of shorts and a t-shirt, come into the lab, put on my heart, put on my mining gear, walk to the lab, and I take a shower. So everybody who enters our lab starts by taking a shower. And essentially, here's sort of a picture of the shower room. But cleanliness is really important. So, you know, we have a car wash. Everything that comes in the lab is washed. And we're constantly monitoring for dirt around the lab so we know where to clean. Oops, sorry. So we are a class 2000 clean room. So that means there still is some dust and such in the lab. But because this is really important to our experiments, it's important that we know what the dust that does exist in the lab actually contains. And so we did a whole study in partnership with Pacific Northwest National Labs in the United States a number of years ago to sort of take an inventory and really say, okay, so the areas in the lab that, you know, that we could collect dust samples from, like what is in this dust? And so we actually know the levels of potassium 40, lead 210, thorium 232, and uranium 238. These are sort of the four elements, I would say, that most experiments care most about in terms of radioactivity. So all of that information, you know, you can get to. By the numbers, we have over 1,000 users of our facility. That doesn't mean there's 1,000 people on site at one time. It means that in the course of a year, 1,000 people use our facilities in some way, or use some of our databases and things that we maintain for the community. 25% of those users are from Canada. They come from 24 different countries and represent 164 different universities and institutions. All right, so let me just give you a brief overview of SNOLAB for those who haven't come there. So basically, this is a picture. You would come into the lab sort of here. So this is sort of where your gowning and dressing areas are. We have a number of caverns, large caverns. So this is the SNO Plus cavern. This is the cube hall. This is the ladder labs. And this here is what's known as the cryo pit. This is a place where we have utilities. And just to kind of give you a sense of the lab itself. So starting with sort of the laboratory facilities, we have a low background counting lab that has a variety of instruments in it and also 2 different experiments. We run 4 different plants underground. So we have a plant for ultra pure water. We have a plant for scintillator. We have a plant that purifies tellurium that is planned to go into the SNO Plus experiment. And then we have another plant, this T-diol plant that takes, because you can't just take tellurium and dump it into scintillator and think it's going to work. You actually have to prepare it to get it to go into the scintillator, like chemically. And so there's this diol plant that's sort of like after you purify your tellurium, it goes to the diol plant where it sort of gets ready chemically to be mixed with the scintillator. Over here, we have a life sciences lab where we have some chemistry that is done underground. We have an underground electrical shop. We have a machine shop underground. So literally, if you're machining stuff underground, you're machining with a vacuum in your hand. It's sort of the dirty part of the lab. In the drift, this is where all the utilities are, including our sewage treatment plant. So we do actually have flushing toilets underground, which is a real treat. Most labs don't have something like that. All right, so kind of talking about the experiments we have underground and where they're located. So in the SNO cavern is the SNO Plus experiment that's currently running and where the future SNO Plus tellurium experiment will be. In the cube hall right now, rather rather than having one large experiment there, we currently have 3 sort of medium-sized experiments there. So Deep 3600, Pico 500, and News G. And then in the cryo pit, that's where we've set the side space for the next generation ton-scale neutrinoless double beta decay experiment, which will either be at SNOLAB, Nexo, or Legend. Going to sort of the smaller sized experiments, in the low background counting facility, there's the flame experiment. This is like a biology experiment. And then we have this CTBT dual high purity germanium detector. So what that is doing nuclear test ban treaty verification. So we operate that and run that program in conjunction with Health Canada. Over here, the ladder labs. So we have the Pico 40 experiment there. In the future, we plan the SBC experiment to be there. We also have the CUTE cryogenic test facility and the super CDMS experiment that are in these ladder labs here. So they're in the labs. The experiments themselves are in this portion of the lab, with their utilities essentially going out in the ladder aspect of it. Over here, we have a little stub. And so essentially, if it is ever that there's funding that becomes available, we may do an expansion of the lab. And if we were to do that, it would be through this stub here. But in the meantime, that's a nice space to park an experiment. So the HALO experiment is sitting there. That's a supernova detector. And this drift here, we call this the J drift. This is where the Sensei, Domik, and this is supposed to say Ascura. I don't know why it says Sensei, but the future Ascura experiment. These are experiments that are essentially using little CCD detectors like you have in your camera to try to detect dark matter. And they actually have some world-leading results from them. So the whole laboratory is 5,000 square meters of floor space. And this whole laboratory that I've described to you is all a class 2000 clean room, 2 kilometers underground. So I actually have a picture where I put it all together. So what you can see is that SNOLAB's a pretty full place. We do still have some room for some experiments in it, but we are pretty maximally at capacity at this time. All right, so on to the next stage, the preview of our strategic plan. The endless human quest to understand the universe is what drives us to continue to seek new ways to push the frontiers of knowledge. SNOLAB itself started as a single site experiment. It was a lab that was built for the SNO experiment. And building off that legacy, it has become this laboratory that I showed you today that's really quite full, it's quite vibrant. And trust me when I tell you, it is a place that people all around the world acknowledge as being a premier site for doing underground science. And so today, SNOLAB is a thriving international laboratory. In our new strategic plan, we're calling Reaching New Heights Deep Underground, and it centers on 3 core pillars. Those pillars are excellent science, cutting edge research infrastructure, and skilled people. Our vision is to be the leading international laboratory in deep underground science, hosting the world's most advanced experiments that provide insights into the nature of the universe. Supporting that vision is our mission. Our mission is to enable world-class underground science, to spearhead research and development, to catalyze scientific collaboration, to promote innovation, and to inspire the next generation of scientists. So supporting that mission then are our core values. Our core values are safety, accountability, diversity, excellence, and teamwork. So on that sort of framework, let me kind of go through the 3 sort of pillars in detail. So our pillar, when it comes to excellent science, our main goal is to drive breakthrough discoveries at the frontiers of underground science. And so what that means in terms of our science strategy is that is centered around the science that we're doing at SNOLAB. And so the science focus of SNOLAB is focused on increasing our understanding of particles and forces that shape the universe. So primarily this means what is the nature of dark matter, and what exactly is the nature of neutrinos. So these two sort of science fields are the majority of the science, and the majority of the experiments that we're doing underground are focused on those two questions. But we actually collaborate with anybody who needs a deep underground clean environment in order to do their science. And so that means that currently we also have neutrino observatories for solar, supernova, geo, and reactor neutrinos. We also do research that studies the effect of radiation on biological systems. And we do some environmental monitoring in terms of nuclear nonproliferation, et cetera. And we're interested in pursuing new collaborations in emerging areas of underground science. And one of those areas that we have just begun starting to do research in is the effect of radiation on quantum systems. And so we recently received a grant from the Department of Defense in the US in conjunction with the University of Waterloo to do some testing of quantum computers underground. So any new ideas? And another big part of our science strategy is to become an intellectual hub that fosters collaboration. And so I just want to advertise, especially for those of you in the room who come to see us often, that we do have this new experimental space with all new furniture. This space is set aside for scientists who are coming to visit the lab. They have a place to work when they're not underground. There's coffee, it's free. You should come visit us. And so we're hoping in the future to be able to assign dedicated staff to assist both domestic and international users in being able to navigate the logistics of being in Sudbury, whether that be housing, whether it be transportation, whether it be reserving a desk space. We want to create a formal user support system that the users can rely on. We've already set aside this dedicated space, and just to say, like, literally kicked out some of the permanent SNOLAB staff that was supposed to go into this space in order to make room for the users. So I really need the users to use it. And you know, by having spaces like this and by providing like services to help with the logistics, we feel like this is really integral to promoting inclusivity in science, to promoting diversity, and to promoting equity. All right, so dark matter. This is where I'm going to move into talking a little bit about some of the experiments we have in dark matter and some of their progress. But I thought I would start by saying a little bit about the evidence of dark matter. So the evidence of dark matter that we have, really all of it is kind of coming to us from astronomy or astrophysical observations. Like, we know the evidence comes from the dynamics of galaxies and larger structures in the universe, all kind of point to the idea that there's this missing mass problem. It's there left over from the formation of the universe, and we see its imprint on the cosmic microwave background. Notice all of this evidence is coming to us from astronomy, right? You know, there's gravitational lensing, clusters, supernova, Big Bang nucleosynthesis. If you take all of this information and you put it together, it tells us something rather remarkable. And that is that about 26 to 27% of our universe is made up of some sort of matter that doesn't seem to interact with light. So it's not interacting with the electromagnetic force. It's not interacting with the strong force. It's interacting with gravity. And hopefully, maybe it might interact with the weak force. There's some theories that tell us that. But the point is we're not able to see it. It doesn't radiate. We visibly haven't been able to see it yet. The search for dark matter and the ideas of what dark matter could be, I mean, it's the space is, I don't want to say it's wide open, but there are a lot of hypotheses out there about what it is. There are lots and lots of theories of dark matter. And so what that means is that basically your dark matter candidates that are plausible could be anywhere from the little ZeV scale up to, you know, tens of TeV, or maybe even 100 TeV. It kind of means that you need a large program to look for these types of particles. At SNOLAB, I would say we essentially have experiments that are looking for particles that dark matter candidates, particle candidates that may have energies somewhere, let's say masses somewhere between 100 MeV, up to, I will say roughly a TeV, maybe 500 GeV. Sort of depends on what you think of these, how specific you want to get. And the way that the experiments that we host at SNOLAB detect dark matter is that essentially you would have your dark matter particle coming in. It would interact with a nucleus or an electron within your detector target and create some energy. It deposits energy. That energy can be measured either by the phonons, the vibrational energy it's giving off. It could be giving off some kind of scintillation. So you could be measuring the light, or you could be measuring the ionization if it ionizes, or you might be measuring out two of these three. And so at SNOLAB here, I've highlighted in blue the different experiments we have using these different techniques or these different handles to measure energy deposits right now. And then I have a few other experiments that are known worldwide that are also looking. The direct detection dark matter experiments are currently the most common experiment we have at SNOLAB. It's our largest class of experiments. And as such, I'm really not going to be able to cover them all. But I do want to talk about a couple of them. And the first one is super CDMS, because they've actually been making some significant progress in our lab. It's currently under construction. So this was in that ladder lab, if you remember. So this is essentially the snowbox, the super CDMS cryostat here. They have a clean room within the clean room. And that clean room is actually scrubbed to have the air that goes into that clean room is scrubbed free of radon. So it's not radon free 100%, but it has significantly reduced radon in that clean room. And there's a whole infrastructure for mitigating the amount of radon that goes into this clean room. We expect world-leading results from even commissioning runs of the super CDMS SNOLAB experiment. And those commissioning runs are of some of the detectors that will be in the Cute test facility. He's responsible for it. The initial payload will have 4 towers of detectors. Each detector tower will have 6 detectors. Those detectors will either be 1.39 kilograms of germanium or 0.6 kilograms of silicon. So each one has a diameter of about 100 millimeters and a thickness of 33 millimeters, so roughly the size of a hockey puck. 2 of the towers are super sensitive to low mass dark matter. They're called HV towers, and those towers have 4 germanium detectors and 2 silicon detectors in them. And 2 of the towers will be IZIP detectors, and they have the 2 towers have 2 different configurations. These IZIP detector towers are primarily deployed in order to help characterize the background that the super CDMS experiment will see. And so mostly what I say is it's under construction. And some of the things that we think are really great milestones for this experiment is that the fridge arrived underground on Saturday, February 4th. You can see a picture here of it nicely constructed, put into its, sorry. Anyway, it's protective coating. I'm trying to think, it's like OVC. Anyway, here's a picture itself of the fridge with Marco, one of the engineers on the project. And then here's just sort of a montage of the fridge being carried underground. So we actually normally don't go underground and work on Saturdays, but for this very special run, because it's so critical, we dedicated a whole day to getting it underground. Let's see here. And then the second big milestone that happened is that 2 of the towers arrived underground on Saturday, May 15th. And so again, a couple of photos of people. VJ here is actually a postdoc at the University of Toronto in this picture, coming, bringing it underground and packaging it, and then getting it into these protective canisters to help, again, keep the radon away from these towers. And then these canisters are sitting inside that radon-free clean room. Another experiment that I kind of wanted to highlight that's a Canadian lead experiment is called the PICO experiment. And essentially, the PICO experiment works a little bit different in that it's essentially a bubble chamber. So the idea is with the bubble chamber is that you can tweak the parameters of the bubble chamber in such a way that your detector response, which will depend on both the temperature and pressure of the vessel, and your threshold can be set such a way that you get different responses to different types of particles. So this is a picture from one of their publications where you can see that for a nuclear recoil, your detector response turns on way out here at a much higher threshold than it would for like a background particle, like a gamma ray. Your dark matter particle, you would expect to have a response that looks something like this. So essentially, by tuning the parameters of your chamber, you can get rid of all your electron-induced backgrounds, so like gammas, electrons, things like that. And then all you're left with is neutrons and sort of anything like lead-210, like your alpha particles, which can be a little bit problematic. So neutrons you can shield against easily by just constructing a shield to put around the experiment. But the alphas are a little bit harder. Essentially what they do to distinguish alphas from what could be a dark matter candidate is they use these piezoelectric sensors. So again, they're kind of using an acoustic discrimination to tell the difference between what might be a dark matter candidate. So a dark matter candidate would look like a neutron, or what would be like an alpha. And they can get really good discrimination with these sensors. So the PICO experiment went through a phase where it was doing some upgrades, and it was down for quite some time. And we were really happy to report that the PICO experiment began regular operations starting this past February. And what you're seeing here are pictures of some of the first bubbles that they started seeing in their chamber after they started running again. So their plan is to collect, I think, like 1.5 years of data before the experiment would be decommissioned. So the future PICO 40 is operating. They have some projected limits that could be world leading. They're also designing and starting to construct the next generation of their experiment, which is PICO 500. The quartz jar is underground. Their design is complete. And actually this I can update to say they aren't waiting for TSSA approval anymore. They have actually gotten it. And once that experiment is up and it's running and reaches its full sensitivity, it essentially will give you a factor of 10 increase in sensitivity over the existing, or over what they project for PICO 40. All right. The last thing I wanted to talk about is these CCD detectors. They're also pretty cool. The really neat thing about these is that they have a lot of advantages. So essentially it takes advantage of the fact that the energy threshold in a silicon band gap is really small. And they also have a very low dark current count, which means that their backgrounds, their internal intrinsic backgrounds are also quite low. And they can access essentially sub-electron readout noise. So these are all really good things for experiments that are really trying to push the boundaries of what they can detect with small depositions of energy. So these types of detectors have access to a variety of low mass dark matter models, including electron scattering, nuclear scattering in the ranges of 1 to 1,000 MeV, absorption, scattering of millicharged particles. The list of these types of ideas for low mass dark matter goes on and on. And so the Sensei experiment released new results they actually, I think, first released them at the APS conference this last April. This I took from Kelly Stifler from the Pheno conference, but they put out some new limits that they have on this sort of electron scattering dark matter. And so the paper is in progress. Hopefully you'll see that soon. So that's very exciting. Let me kind of quickly go through the neutrino program. So I had mentioned this HALO experiment. HALO turns out to be the longest, most stable running experiment that we have at SNOLAB. It just sits there, it takes data, and it's waiting for the next supernova explosion that happens in our galaxy. It's 79 tons of lead blocks. They're instrumented with 128 tubular helium-3 neutron detectors. They're hooked into the SNOOS network. And like I said, it's the longest running experiment that we've had at SNOLAB. So I think it deserves a mention because of that. SNOLAB's also really excuse me, interested in neutrinoless double beta decay. Again, just kind of briefly going over the physics of this. So we know that that 2 neutrino double beta decay is allowed in some isotopes. So it involves the transformation of 2 neutrons into 2 protons with the release of some neutrinos. If it so happens that neutrinos are Majorana particles, then the idea of neutrinoless double beta decay can happen, where the neutrino is not released. And so essentially the 2 neutrino double beta decay is represented by this peak. And then sort of this peak here shows the signal that you're looking at for this neutrinoless double beta decay signal. So it's something that's very hard. You need good energy resolution and good separation, if you can, between the 2 neutrino peak and the neutrinoless double beta decay peak. I really like this plot by Jason Detweiler. So it basically shows if you have a more rare interaction. So this is the half-life for a 3 sigma detection in years versus your exposure, your detector's exposure in 10 years. And it tries to illustrate for you the importance of having really the lowest backgrounds you possibly can achieve. So this band here is supposed to represent essentially your neutrinoless double beta decay signal under a certain assumptions, okay? So the idea is that if you are background free, your half-life or your detection probability, if you will, versus exposure follows this line. If it is that your background in your region of interest is 0.1 counts per ton year, then your background your sensitivity goes as this line here, this dash line. If it's 10 counts in the region of interest per ton year, your sensitivity goes as this dotted line. So you can see that with 10 ton years of exposure, the difference between 10 counts per ton year and 0.1 counts per 10 years is your difference between being sensitive to the neutrinoless double beta decay or not in this model. These experiments are really, really difficult. At SNOLAB, so at SNOLAB, just showing the sensitivity, I feel like I missed, okay, I guess it. So SNOLAB actually has sort of 3 experiments that are going on or being considered at some point. So there's the SNO Plus experiment, which has 2 phases, the Legend experiment and the Nexo experiment. And this is just kind of showing, this actually comes from a study done in the United States of the future of these sort of neutrinoless double beta decay programs in terms of the whole nuclear physics program in the US. And you can see that, you know, Legend and Nexo and SNO Plus, they're all here. So these are existing experiments that are running now. And then the open boxes are planned experiments in the future. So SNO Plus, this is just a picture of the tellurium plant that we have underground. So they plan to add 1,000 kilograms of 130 tellurium to their detector so that they can have sensitivity to the inverted mass ordering. The tellurium plant has been installed, and we're currently working on commissioning it to do a test batch of purifying this tellurium. It's the first step to loading that tellurium into the scintillator. But one of the things that I want to say that's pretty cool about SNO Plus is that they have a phase detector. So for a while, they were running in their detector balloon, if you will, just pure water. And they were running with just pure water. Currently, they're running with just pure scintillator. So the water's been drained, and they now are running with pure scintillator. They recently did an analysis looking for antineutrinos from distant reactors in this pure water phase that they did, and they observed it. And it's the first time that that had been observed in water. And so that was kind of really a neat and exciting thing. So I said it's currently operating with the liquid scintillator. The water phase is complete. They had that first result with the reactor neutrinos showing that everything was working really, really well. They're also setting limits on invisible nucleon decay. They're planning to try to measure boron-8 neutrinos in that medium. The pure scintillator phase is ongoing. Again, they're looking to get some physics out of that phase as well, including detecting low energy boron-8 neutrinos. Again, looking at those reactor neutrinos and geoneutrinos, and actually they're not neutrinos, but they're the anti-neutrinos. A supernova, neutrino, if a supernova goes off, they'll be able to see neutrinos from that. All right, and so very quickly, I want to just summarize some of the biology. Let me just I think this is kind of cool, even though I know you're not physicists. This is a picture of that chem lab that I was showing you underground, and the biology experiments are there. So the idea is there's this hypothesis, like we know that if you go out into outer space or you're up in a plane, like we know that having an exposure to a lot of radiation is not good for you, and it's not good for your cells. And there's a question of what happens if you have too low of radiation. Like, so too much radiation is bad for you. Is too little radiation bad for you as well? Is there a sweet spot by which having a little bit of radiation and exposure to it can be good for you and your cells? So it's an idea of it, is there a sweet spot for the dose of radiation that you should receive? And this by far, I'm not saying go, stand and get yourself, radiated. It's like, just maybe you shouldn't take all the radiation away. And so basically the idea is that you take the human cells with your sub-background environment that you would have underground and you grow them. And the question is does it have implications then for cell growth, DNA damage, and ultimately carcinogenesis? I don't think I have a slide after this, but I can tell you that the first studies that have come out from this actually validate the hypothesis that indeed too little radiation is not a great thing for the evolution of your cell growth and DNA damage, but follow-up studies are going on. So the first results from these types of experiments have been published. Excuse me. All right, so I'm not going to go through this slide. This slide was just meant to be like, I could only cover a few topics, but we do tons of science at SNOLAB, and we're always looking to do more. So let me talk a little bit more about what we're doing to continuously improve our research infrastructure so that we remain state of the art. So in the next 6 years, we're hoping to fully explore the potential of our cryogenic systems. So this is going to require us to scale up our underground production of liquid nitrogen, our capacity to do so, especially if we're going to host some of these large neutrinoless double beta decay experiments. We need to be able to produce more nitrogen underground than we currently do. And we want to further develop innovative testing facilities for quantum computing and quantum technologies. We want to continue to innovate new tools and technologies for low background experiments. That primarily has to do with expanding this low background counting facility that we currently have. We need to continue to upgrade our operational facilities. In particular, we want to be looking at using automation wherever we can. It's especially important when you have this underground facility that as much remote monitoring and automation you can do as possible and nobody's there to deal with it right away, like at night or on the weekend. It takes a significant amount of time to get underground, walk to the lab, take your shower, get in to take care of it. So the more we can do with remote monitoring, the better. We want to continue our focus on safety and sustainability. And we're really working on, we're calling it exporting our underground infrastructure expertise around the world, but we are working with a lot of underground laboratories around the world, both who are thinking about developing or expanding, and just we want to increase the capacity to do underground science everywhere. As much as I'd like Canada to keep the marketplace on it, we can't do it all. So let me give you a few highlights. We have, and I'm not going to go through this whole slide, but we have a significant amount of instruments for assaying materials that experiments use to build their experiments. We also have an arsenal of different types of counters and detectors that we use to do measurements of the backgrounds that are already in our our underground facility and our surface facility. Radiopurity.org is a database of measurements made of all sorts of different types of materials by facilities all over the world that's hosted at SNOLAB. So this is something that we are currently maintaining in partnership with Pacific Northwest National Laboratories, but it is physically located at SNOLAB. And I really encourage you, like if you want to use your computer or phone right now, you can go online and check this out and try like looking up copper and seeing what you get. I fully encourage you to use that and be rude if you want to. The underground liquid nitrogen plant has been operational since last May. It produces high purity liquid nitrogen at a rate of 3,000 liters per week, and we use that nitrogen throughout the lab. And then this is just additional infrastructure. So it's actually really hot underground. It's really warm. And so we provide cooling of the laboratory itself, in addition to power and cooling for the entire lab and all of the experiments. We have a backup generator. We have purified water, purified liquid scintillator. We have networking, wet chemistry, and a machine shop underground. On the surface, we have laboratories for assembly and chemistry. We have offices, meeting rooms, auditoriums, etc. Everything you would want in a lab. So the final 5 minutes, the final 2 minutes, I want to talk a little bit about our people, because, you know, the science is really awesome and it's really cool, but what makes SNOLAB and what makes Canada so special is the people who are doing the work. And so I find SNOLAB to be a very welcoming place, and we're not perfect, but we're trying. We're trying to be better. And we really want to embed equity, diversity, and inclusivity into everything we do. And so when I was back talking about research and how we want to foster collaborations, that's about equity, it's about diversity, it's about inclusivity. And so we are working really hard towards gender parity. And we are creating wellness spaces in the surface building and underground. So in the surface building, we have the space identified and we started outfitting it. Underground, it's going to take us a little bit more to get to where we want to be. We are creating an EDI commission. We had an EDI task force that met previously a couple of years ago and came up with some really great recommendations. And now what I'd like to do is make that more of a standing committee, have that committee report directly to me. We want to increase our professional development and training programs. So for SNOLAB, what that means is that we have this very successful engineers and training program, and we want to make that, we want to formalize that more. We also sometimes work with skilled trade apprentices in order to help them through their programs too, to get their certificates to move through that process. We have a very successful SNOLAB student training program where you're getting a view here on the screen of some of the people who were in this last year's cohort during the CAST competition. And essentially the institutional support we have for community education and outreach, professional development efforts, conferences, workshops. There's a number of things that we sponsor and support, and we plan to continue to do so. And finally, we want to beefen up and strengthen even further our public engagement and focused efforts on K through 12. And here, rather than reading you the slide, I just want to point out, this is actually a cosmic ray cube. So this cube is detecting cosmic ray detectors. These cubes were built and in a partnership with Gran Sasso Laboratory, so LG&S in Italy. We're working to think about how it is we might network this type of cube as sort of maybe a global type of program, create interactive ways that perhaps that we could get interactive exhibits that people could interact with, either while they're visiting the Science Museum or while they're maybe teachers in their classrooms. So we have lots of ideas of how we might further use this instrument in cooperation with a worldwide effort to, connect students around the world. So with that, I'll go to my conclusions. And since I think I am now out of time, I won't read them all to you, but I do hope that I leave with the impression that SNOLAB has a broad, multidisciplinary science program, and I really hope to see you and your experiment in our lab soon. Thank you.